bit. I also prepared the slides which explains the standard model, but I think that you're quite good level, so you don't need it. So let me just jump directly to the Atlas and LHC. And in principle, what I also would like to do, I will show you some results that we have right now in Atlas experiment. And I would like to describe you these results, but if you don't understand, please ask me. If it's even stupid questions, there is no stupid questions, okay? So please ask, and we can also talk about it, what in principle we measure and why it's so interesting, and we are so excited. And okay, so let's start. Let me just take. Okay, I think that this picture you already saw, I don't know, hundreds of times or millions of times, right? So I will not spend my time. So you see the LHC accelerator, we accelerate protons. Right now we accelerate the energy of the protons 3.5 TeV. Do you know where we would like to come, to which energy? What is the designed energy? 7 TeV, right, yes. This is actually our plan, our future plan, but it's impossible right now. We have a problem with the magnet, therefore we start with 3.5. Okay, and then we have 4 different detectors on the LHC. We have two general purpose detector. What does it mean, general purpose detector? Any idea? No, we have a proton, and this is what we have in LHC. It's a proton-proton collision, okay? But on the LHC we have a 2 general purpose detector. What does it mean, general purpose detector? It means that you, any idea?
It looks for whatever comes.
Exactly, yeah. I mean, with this detector we can measure everything. Any type of physics. We can do B physics, physics of quark B, we can do quark top physics, we can search for new physics, we can do standard model physics, okay? So therefore we call general purpose detectors. So we have 2 general purpose detectors. Do you know which kind of detectors is a general purpose detector? First of all, Atlas, the biggest one, right? The important one. And then we have CMS. So what is the CMS? It is the heaviest detector. Okay, so we have 2 general purpose detector, and then we have, which kind of detector we have? We have LHCb. What's so special with LHCb? It's a B physics, right? It's a focus on the B physics, and then we also have a Alice detector, right? Which is a purpose. What is the purpose of the Alice detector? It's a nuclear physics and plasma. Okay, so you know about it. So let me move to the Atlas. So this is the Atlas detector. Okay, so let me just explain you what we see. So this is the interaction point. Okay, and the beam line is here. And then it's just layers of the different detectors. We already know that we have a different type of detectors in order to detect different type of particles, right? Therefore, we put like layers in order to detect everything what we have outside, I mean, in the interaction point. So we start with a track, you know what, I actually have this slide after, so let me just try to see what I have. One second. Okay. Sorry. Okay, so we start with the inner detector tracker in order to reconstruct or detect charged particles. Okay, we have it inside, the yellow one. And this is actually a charged particle. It means electrons, muons, pions, kaons, protons. So this particle we can measure. Then we have a calorimeter. We have 2 different types of the calorimeter. We have electromagnetic calorimeter. What we can do with electromagnetic calorimeter? Yes, electrons and photons, right? And how we do it? Exactly, energy deposition. Okay, and then we try to collect energy deposition and estimate the energy in the calorimeter from energy of the electron or photon. And then we have a muon spectrometer. So all blue part that you see is actually muon spectrometer. And we also, this is actually Atlas jargon, we say that this part and this part is the end cap, and this is the barrel part. Okay, but this is the Atlas jargon. So we have a 6 stories high, 50 yards long, weighs 7,000 tons, 800 baseball players, 2,000 physicists, and of course cost.
Excuse me, how
Yeah.
big is a baseball player? Well, there's 7,000 tons, 800 baseball players.
You can divide and measure the mass of each one.
That's like 900 or something. Yes.
Maybe it should be 8,000.
It depends, because each one probably needs a space. I don't know. The private space. Okay, let me move on. So actually, once I'm talking about Atlas experiment, I used to compare the Atlas experiment to the bubble tower. So what is the common between bubble tower and the Atlas experiment? That we have 2 multinational projects. We have a large labor force, speak different languages, and ambitious goals and best technologies. And then building the Atlas detector, 6 things a detector be capable of doing: measure direction, momenta, sign of charged particles, measure energy of the carried away by electron photons, measure energy carried away by hadrons, protons, neutrinos, pions, determine point of origin of charged particles, infer the presence of undetectable neutral particles, calculating missing energy as you said. And find 100 potentially interesting events of the 1 billion that occurs every second. And then we use a trigger system. Okay, so Atlas, like all over accelerator-based detector, is constructed in layers, as I already said. So let me just repeat detector technology, just that it will be clear to everybody. So we have electrons. So we have a signal in the tracker, and then we have also signal in the calorimeter. Okay, it's clear to everybody. Then we have photons. We have a signal only in electromagnetic calorimeter. We don't have anything in the tracker. Then we go to muons. Okay, we have a signal in tracker and also in the calorimeter, but mostly in muon spectrometer. And also what we have, protons and pions. We have a signal in the tracker and in the calorimeter. And neutrons. We have a signal in calorimeter, hadron calorimeter. Okay, and we can actually see it in the, once we turn on magnetic field. Okay, this is how it looks like. Okay, and I go back to, any question? I go back to the Atlas detector, and again, I show the inner detector, electromagnetic calorimeter, hadron calorimeter, and cup and barrel toroid magnets, and blue, it's a muon spectrometer. This is, by the way, this is what we discussed in the previous hour. This is these tubes. I just put it here in order to show you that actually what we learn because we use it in Atlas. Okay, not only in Atlas, we use it in different detectors, but especially in Atlas, we use these tubes in order to reconstruct muons. And these tubes came from this part. Okay? Okay, and then I would like to show you just several details, but it's not very, very important from the, which is related to the inner detector. So we use 3 different technologies: detector, semiconductor tracker, and transition radiation tracker. And by the way, the pseudorapidity, it's, let me show you. Once I say pseudorapidity, I have to demonstrate what it is. So this is actually pseudorapidity. It's like in this direction we measure, okay? So here the pseudorapidity, this is the pseudorapidity 0, and this is the pseudorapidity, here is approximately 2.5, Okay, so we have a coverage up to 2.5. So once I put similar rapidity here, it means that I just would like to demonstrate the coverage of this detector. So we have 3 different technology, and I also put here the pictures from the insertion of the different detectors in Atlas. So this is installation period. We cannot see it right now because everything is closed. Okay, and this is, I assume, it's a difficult part for you, but I try to be very slow. So this is actually, we try to reconstruct particles that we know. We know that this particle exists, and we try to reconstruct it and to see the resonance. And it provides us confidence that our inner detector works very well. So what actually we see? Here we see invariant mass distribution of 2 pions. Okay, pion is a charged particle. Okay, so it means that we have 2 tracks in the inner detector. We have a lot of tracks. Okay, many tracks. So we search. We take the 2 tracks and we calculate invariant mass of these 2 tracks, and then we plot invariant mass of 2 tracks, and this is actually what we see. But it's not the whole story. Okay, if we will do it, we will not see any peak. We will not see any bump of K short. So we need something special of this particle in order to distinguish this particle from the rest. Okay? And what we know about this particle is that it's a long-lived particle. Long-lived particle, it means that once you reconstruct the track, they come not from the interaction point, but they came from some point in the middle of the inner detector. So we can apply the distance between primary vertex and the secondary vertex in order to reject the noise. Okay, let me just probably try to draw. This is Z, R. Okay, so this is, for example, the inner detector. So normally we have a track from the interaction point, for example. Okay, this is a normal track we have. In the case of the K short, or in the case of lambda, it's a 2 long-lived particles, so they actually decay inside the detector, like this. Okay? So we reconstruct the secondary vertex, we call it secondary vertex, and then we apply cut. We say, okay, we reconstruct the secondary vertex, and then we apply cut on the distance between primary vertex and secondary vertex in order to reject background and in order to reconstruct these 2 particles. And yes?
What is your data that matches simulation?
So what actually you see here 2 things. So the first of all, you see data, and the second thing, the yellow one. By the way, I think this is a problem with the fact that I use MAC, because it should be all yellow. Okay, because a yellow shows simulation. So what we wanted to do in the beginning. Okay? In the beginning, we have our data and we have a Monte Carlo simulation, right? And we would like to, first of all, to check that our simulation works properly. Therefore, we would like to compare our simulation with the data. And this is what we are doing. Okay?
So it does match them on the...
It matches, yes. We have a very good match. It means that we understand what we are doing. We take everything into account. So first of all, we check the position. Okay? We check the position, this is what we measure. We check the position, we take this number, we go to PDG, because it's a very well-known particle, right? And then we compare to what we see in the PDG, and we say, great, it means that our detector works. Okay?
Is there a background in this plot?
What?
Background.
Background?
Is there a background in this plot?
Of course. So you see, this is a K short, okay? And all this part, it's actually background. This is a background, and this is a background. And even if you take, for example, cut on the invariant mass, okay, and you take the particle from here, still there is a probability that this particle not K short, because you have also background. Okay. But yes, what you see here, we call it a K short candidate or lambda candidate. So you have a background and you have a candidate. Okay, let me move to the next slide. Okay, the next slide I present Z particle. So this is actually what we see in the event display, Atlas official event display. And what we can see here is when Z particle decay to 2 electrons. Okay, so it's already not inner detector track, it's electrons. So we have an inner detector track, and then we have also information from the calorimeter, and we say that the particle is an electron if we have a match between information from the calorimeter and information in the inner detector, and then we calculate invariant mass and check if it came from Z or not from Z. So let's see what we have. So this one, actually this is a tracker. So the yellow one, you can see 2 electrons from the 2 electrons which pass through tracker. And then you actually, what do you think? This is what? Any guess? So this is the calorimeter, the yellow one. Sorry, not yellow one, the green one. The green one is the calorimeter.
H.
What?
Is it H color or?
No, this is electromagnetic calorimeter.
Which?
This is electromagnetic calorimeter. So my question, what it is?
Photo.
We are talking about 2 electrons. So this is actually what we see. This is the energy deposition in calorimeter, right? From 2 electrons.
Where is the H color?
Hadron calorimeter, I think it's this one. This is a hadron calorimeter.
So there is a space between E cup and H cup?
Yes, it should. I mean, there is some space. Yes, I assume. I don't know exactly what space, but there is a space. Yes.
When does the shower continue?
Sorry?
When does the shower continue? Like from the observation?
No, it doesn't continue. This is the main point. So we have an electron. An electron deposits energy in the calorimeter, and this is what we see. So it deposits all energy in the calorimeter, and it means that we can actually calculate the energy of the electron.
Why don't hadrons deposit energy in the E-count?
Sorry, what's the question? I couldn't hear.
Why don't
What?
hadrons deposit energy in the E-count?
Okay. But you have followed the QCD lecture. You should be able to answer. Yes?
No. I think I follow easily, but I guess not wrong.
The question is why the hadrons are not depositing their energy in the electromagnetic calorimeter?
Well, maybe they do, but they just pass. I mean, it's a small deposition.
Yes, exactly. They do, but it's a very small deposition.
They don't stop at least.
Exactly.
Because of cross-section values.
Is there a lot more material in the H count to stop the hadrons?
Yes. Yes. So, I mean, what I wanted to demonstrate, let me just come back. I think that we just moved from this point. So what I wanted to demonstrate is that here you can see that we have 2 electrons. Okay, this is, by the way, this is the Z position and this is the R position. R direction, sorry. Z direction and R direction. So what I wanted to demonstrate is that we have 2 electrons, and once we calculate, and you can see the same electrons but in the phi plane. Okay, so this is the RZ plane, and this is the phi plane, X, Y plane of Atlas. Okay, so in principle here you see exactly the same, so that we have an inner detector track, and then we have an energy deposition in electromagnetic calorimeter. It means that we have 2 electrons, and then we calculate invariant mass of 2 electrons, and invariant mass is approximately 89 GeV. It means that this is a good Z candidate. Okay, any questions? Is it clear what I try, or is it too, I think it's probably too much what I try to present here.
What are the rest of the tracks in the tracker?
It can be pions, kaons, protons, muons.
Where do they originate from? Like if they even just only set to E plus, E minus, is there an underlying event or pileup or?
No, in principle, I think that this is what you see. It's a Z plus jet. It's inclusive Z production. So you may have a Z plus jets. It means that you have a pions, a bunch of pions and kaons, and this is what you see in calorimeter, in the inner detector.
So it's from the proceed, like the interactions occurring with that creates the pions, the rest of it.
Yes, we also have different particles, right? Yes. Okay, let me move to the Muon spectrometer. I already discussed a little bit about it, but I would like to show you again. So this is just geometry of a Muon spectrometer. This is a phi plane, and this is a RZ plane. Okay, again, this is the interaction point direction, Z direction, R direction. And we have 4 different technologies for Muon spectrometer. We need 4 different technologies because we have 2 different types of Muon spectrometer. We have a Muon spectrometer for triggering. We already talked about it. In order to say that we have Muon. And then we have 2 types of detectors for precision measurement in order to measure precisely momentum of muons. And then actually you can see that we have layers of the Muon spectrometer in end cup. Again, this is the end cup area, this is the barrel area. So we have layers of Muon spectrometer in the end cup. And you understand now why we have different layers, right? Because we would like to, in principle, we need a sagitta. In order to calculate the momentum, we would like to calculate sagitta. And in order to calculate sagitta, we need magnetic field and we need space, right? Therefore, we actually put layers far away from each other in order to see the bending of the muon in magnetic field and calculate sagitta. Okay, so we have layers in the different Muon spectrometer in the different layers in end cup and in barrel. Okay, and this is actually how it looks like. This is the pictures of Muon spectrometer of the big wheel, and this is just example. This is the trigger chambers, and this is the MDT chambers, precision chambers, Muon spectrometer. So this actually the tubes that we discussed today. This is actually the white tubes you see here. So these detectors we use for triggering, and these detectors we use for precision measurement. Now here you can see the barrel part. So here you again see Muon spectrometers, the layers of Muon spectrometers here, and this is a barrel toroid which produce magnetic field. And this is a magnet. I just demonstrated we have 3 different types of magnets. We have a barrel toroid and cup toroid and solenoidal magnetic field. And okay, I just put doesn't matter. Let me just continue because we don't have time. And this is again the picture of the barrel toroid. This one I think we don't need. Let me skip this one. This is just present again this principle. Okay. So these tubes, again, you see this picture of the Muon spectrometer. I just talked a lot about Muon spectrometer because I worked many years for Muon spectrometer, and I thought that it's like my baby. I would like to talk about it and share this information with you. But of course, we have many very important detectors in Atlas. Okay, so here, these actually tubes came from here, and let me see. And we have a magnetic field. So this is just shows you the direction of the magnetic field, and then it just shows that we have a different layers of the Muon spectrometer. We call it inner station, middle station, outer station, in end cup and in the barrel. And then we have a muons. Muons pass through different layers of the Muon spectrometer, and we can, yes?
Sorry, why can't we stop the muons? We can stop electrons, protons, yes, I understand they are charged, and muons are charged too.
Yes, but we don't want to stop them. We have a Muon spectrometer to measure why we cannot, why there is no energy deposition of the muons in calorimeter. So we have a deposition. We have a deposition of the muons in calorimeter, but muons, it's a heavy particle. It's heavier than electrons, and they actually pass through calorimeter. We don't have a material which actually can stop muon spectrometer. So we do have a signal in the calorimeter, but it's not enough to measure the energy. It can help us. It's in principle in the reconstruction. It helps us, but it's not enough.
So how do we estimate the full energy of the muon?
The full energy of the muon.
Yeah, we can't extract it, right?
Yeah, you remember the formula I presented in the first hour? That we calculate sagitta.
Yeah.
Okay, and in the sagitta we have a velocity. Okay. If we have a velocity, it means that we can measure momentum. If we can measure momentum, it means that we can measure energy. Okay. So it's two different principles. Okay.
Comment to the previous question. In the simulation lecture, you were suggested that you read the PDG book. Yes, there's a section about ionizing particles and energy loss by ionization. There it's written why and how long a wall you need to stop like this. Why don't you read it tonight and before class tomorrow?
But it's important to remember that we do have a signature in the calorimeter from the muons as well. Especially it's important to remember once you write the software packages to reconstruct muons, and it can really help. So this is quite important. Okay, let me show, this is just demonstrate the position of the trigger chamber. Okay, now we came to, so you know that Z decays to leptons. So leptons, it's muons, and electrons, but also muons. So in principle here I just demonstrate the example 1Z decays to muons. Previous example was with electrons, right? So what we saw? We saw the trapped and energy deposition calorimeter. Now we are talking about two muons. So what we see? We again see tracks, right? Because it's a charged particle. And what else we see? We see the tracks on muon spectrometer, right? We see the tracks, you see this one, which pass through 3 layers of the muon spectrometer in the barrel part, and we see here that this muon, it's quite high energetic muons with a momentum 27 GeV and 45 GeV, it passes through layers in end cup. And then we calculate sagitta, we measure sagitta, sorry, we don't calculate, we measure sagitta, we calculate momentum of muons. Once we have momentum, we can calculate invariant mass, and to check invariant mass and to say if it's a Z candidate or not Z candidate. Okay, let me come to the W. Okay, I will just try because this is, I think it's too complicated. So this is just example. Once we, do you understand what does it mean W particle, that it decays to 2 leptons, but one visible particle, it's a muon, and the second one, it's neutrino. So what happens in this case? How we are going to reconstruct this particle? What in principle we see in the detector? Any idea?
Momentum will not be conserved, since we can see it.
Yes, of course. So we don't see neutrino. It means that in principle we cannot reconstruct this particle, right? So we see only, in this case, we only see one muon. Okay, this is what we see. We see that we have a high energetic muon which pass through different layers of muon spectrometer with energy 40 GeV. Okay, so what happens? How we can distinguish? How we can reconstruct W particles?
Missing PT for neutrino.
Exactly. So in this case, if for example you would like to reconstruct W's or particles which decay to one visible particle and one invisible particle, like in this case, so in this case we calculate the missing energy. Okay, so missing energy, it's something that we know the energy conservation, right? We know that we have energy in the beginning, so we expect that there is an energy in the end exactly the same, and if we have a neutrino, it means that we miss something, and then we calculate what we miss, and then using this missing missing energy, we can actually reconstruct W particle.
What happens if the segment of the detector isn't working properly, so you miss extra energy back?
This is very, very good question. Therefore, we work very, very hard already 2 years in order to identify these holes in the detector of problematic electronics which doesn't work. So what happens in this case? In this case, we need a lot of data, first of all, because if we don't have data, we cannot say that this part detector doesn't work. Okay, so we need a lot of data. We collect data. This is what we did last summer. We collect data, and then we build the maps. We build the maps and we see, there is nothing in this region. What happens? Something doesn't work. The detector doesn't work, or it's a problem with the electronics, or it's a problem with the reconstruction, or it's a problem with something, okay? So we try to understand, and then once we come to the point that, if the detector doesn't work, so we try to replace it, or to fix it. If it's impossible to fix it, it means that we have to take it into account in our calculation, okay? So first of all, we take this kind of, problem, and we propagate it, we take it into account in our simulation. Okay? And we have to take it into account.
So you just kind of correct it on average?
Exactly, yes, we correct. Of course, missing energy. So it's a fact, once we will see a long tail of the missing energy. We see some kind of extra missing energy because of these problematic regions. Okay? But it's very important to correct, especially once we are searching for events with a large missing energy, new physics events. So we have to do this calibration work, and this is very hard work. Okay, so this is more or less all what I wanted to present, and as I said, you're welcome to ask me questions, and good luck. Yes?
How can we distinguish the events? I mean, we collide proton and proton, and there will be lots of, Zs and many other particles, and they will decay. And how can we find the W proton, for example, from that?
Okay. So I assume that you asked me the question about trigger system. By the way, you have an expert here, which is a HLT expert or trigger expert, so you these kind of questions you can ask him. But I can try to answer your question. So in principle, first of all, we have to we don't want to take all events because we have many events without any interesting information. Or for example, we have events once we don't have high PT physics or physics that we would like to investigate. Okay, so first of all, we have to say, okay, I have this event, but I don't want to write this event, to record this event. I would like to take only event which is interesting for me. For example, event once we have at least muon, high energetic muon, or high energetic electron, or something interesting. Okay, and the rest we try to reduce. So for this purpose, we use a trigger system. It's a very complicated system in Atlas, and we try to do it. It should be done very fast because we have a really very high rate of data. And we have a different layers of the trigger. We have a hardware trigger and we have a software triggers and more complicated triggers. So for example, how we can reconstruct what you ask, reconstruct what?
I mean, how can we identify the particles or which events?
So first of all, we record events which is interesting for us, okay? Which actually includes some important information or some physics which is, therefore we identify electrons or we identify muons. If there is nothing, so we don't record this event. So then we take this event and then we check if there is something specific, more interesting, some physics. For example, I would like to collect events which includes two muons in order to reconstruct the particles. This is something that I presented you here. For example, this one. Okay? So first of all, we have to see that this event includes two muons. Okay? So if, for example, first of all, I saw this event includes one muon, So we record this event. Then we go to the next step. Then we require, for example, that this event includes two high energetic muons. So we actually select this event further. And then we try to reconstruct, once we have two muons, we try actually to reconstruct Z particle or some more complicated particle. But we start from very small elementary particles, for example, muons or electrons. It also depends which kind of physics we would like to do.
So for every event we want to look, we take different data. Is it right?
We can say tomorrow and until the end of the week, we will be reconstructing objects. We will be running analysis software. Just hang on there.
Okay.
We will do that.
This is very
yes, I will tell you this.
Okay. But we can also talk, after, and I can try to explain what exactly we are doing. But if you will have this exercises in this lecture, so I think that you will understand better. So, more questions? Okay, so thank you very much, and you're welcome to ask questions after my lecture.
Did you figure out why? So, did you figure out why? How long were you? Yeah. Remember,